Welcome to the first lecture of 8th week. In this week, we will start discussing about a new class of smart material, that is shape memory alloy. At first, we will see the behavior of this shape memory alloy. We will see what makes this material smart, and then we will talk about their mathematical modeling, I mean the constitutive relations, and after that we will see some applications and we will see the corresponding formulations. So first, what is shape memory alloy? Shape memory alloy is a material that memorizes its original shape, and these materials show phase transition or phase transformation, and through this phase transformation the shape memory alloy, the shape memory effect is seen, and this phase transition happens through heat or stress input. Now here the transformations are in solid states, so here it transforms from one solid phase to another, and we see large deformation can be restored through it. So in case of nitinol, which is one type of shape memory alloy, around 8% of deformation can be restored. We will see in details what this means, what the restoration of deformation mean, what is meant by phase transition as we progress. And these materials can take significant stresses without undergoing permanent deformation. So shape memory alloy shows two type of special behavior. One is shape memory effect and another is pseudo elasticity, and this is its undeformed shape. And suppose that we give it some deformation and we deform it in some fashion, maybe deform it to this shape. Now this deformation is large, so if we remove the load, this material does not go to the previous original shape, so some deformation remains. So it's kind of plastic deformation. But if we give heat input to it, if we heat the material, then upon actuation by heat, this material regains its original shape. So this shape and this shape are same. In the meantime, this shape is different. So we get this shape by applying force, and then by applying heat, we regain the unstressed shape. So in some sense, this material, although here the deformation seemed to be permanent, but it had its previous shape in memory. So under heat actuation, it could regain its previous shape. So it's shape memory effect. Now there is another effect called pseudo elasticity, that is called sometimes super elasticity also. So under some conditions, under some temperature condition, under some stress range, the stress strain behavior of this material looks like this. So the loading path is this, while unloading it comes back through this path and it comes back to where it started. Now because after unloading it came back to where it started, so it is kind of elastic behavior. But here the behavior is hysteretic. We can see that the loading and unloading path are not same. So this kind of behavior is generally associated with energy dissipation. So this is called pseudo elasticity. Now this shape memory effect make these materials a good candidate for use as actuator, because we can always keep the material in this kind of deformed configuration in the structure, and by giving heat input it will try to regain its original shape, and that will generate actuation force. And here, because we can see energy dissipation, these are ideal material for use as damper. So vibration isolation, energy dissipation, all are different application of the pseudo elasticity, and actuation is the application of shape memory effect. So this pseudo elastic effect was found first in gold cadmium alloy by Arne Olander, that's in 1932. Then in 1951, Chang and Reed observed shape memory effect in gold cadmium alloy, After that, in 1963, Buehler and Wiley observed this shape memory effect and pseudoelasticity in nickel titanium alloy called nitinol, and after that the tremendous development in this field started taking place. So Buehler first observed that an alloy which has titanium and nickel in almost equal proportion shows some phase transition at different temperatures, and those are the phase transformations that leads to shape memory effect. And they also observed that by varying the proportion of these constituents, the transformation temperature can be varied. Now there is a nice history given by Kaufman and Mayo in this article, and that is presented in the book by Srinivasan and McFadden also, of how this material was invented. So Buehler was a metallurgist in Naval Ordnance Laboratory, and he was looking for potential good materials for use in cone of a missile. So out of around 60 materials, he sorted out 12 materials and tested it, and out of those 12 he found that an alloy of nickel and titanium shows good impact resistance as well as good fatigue property also. So he named this material nitinol, nickel Ni, titanium Ti, and Naval Ordnance Laboratory NOL, nitinol. And then they started doing further experiment on these materials. So they casted around 5 bars of this nitinol in their furnace, and they left it for cooling. Now when one of the sample was cooled down, he wanted to take it to a different place for some surface treatment, grinding, and then while taking it, he dropped it. It was dropped on the ground, and he observed a dull sound from it, dull thud. But then he tested other materials at different temperatures, and he observed various other sounds. So those at higher temperature was observed to show more of metallic sound. So that was very interesting observation, and finally after doing various tests, they concluded that these materials undergoes some atomic structure rearrangement, some phase transition at different temperatures, and that is showing this various behavior at various temperatures. And after that, series of experiments, series of work have been done in this area, and the theory of shape memory alloy has got a good amount of maturity, and that's what we will discuss in this course. Now shape memory alloy are generally, there are around 20 alloys that exhibit shape memory effect and pseudoelasticity, and these alloys have generally 2 or more of these materials as constituents: aluminum, cadmium, copper, gallium, gold, manganese, nickel, titanium, zinc. Here shape memory effect is again shown. So this we can think to be the initial configuration, and after force application it is deformed to some shape, and then again by heating it regains the original shape, and again if we cool it, it remains in this shape. Now nickel titanium alloy is one of the most widely used shape memory alloy. These alloys can recover up to almost about 8% strain. So if the amount of strain is about 8%, it can be recovered by heating. This material shows super ductility, they have higher resistance to corrosion and abrasion, and they have higher tensile strength. Now this shape memory effect comes into picture because this material remains in one of the 2 phases depending on the temperature and temperature history, and these 2 phases shows distinct material behavior. For example, Young's modulus, there can be around 200% variation of Young's modulus in between these two phases. Other that is in case of nickel titanium alloy. Other shape memory alloys examples can be copper aluminum nickel, copper zinc aluminum, and so on, gold cadmium and so on. And the strain recovery is between 3 to 8% depending on the alloy. The material properties depend on the chemical composition, cold work, heat treatment. These are the processes that are generally followed while manufacturing, and thermomechanical cycling. And the material behavior depends on internal crystal structure, stress, temperature, and history of the material. So just stress and temperature is not sufficient to know the present behavior of the material. We also need to know the history of it, how the stress was before, how the temperature was before, because this material shows something called path dependent behavior, and we will understand that as we progress. The advantages of these materials include large force output to weight ratio, large stroke, because we have seen that they can be strained up to 3 to 8% depending on the material, and that amount of strain can be recovered. So there is large displacement, large force when the material tries to recover the shape. And there is large specific energy density, and it offers flexibility in design because here the actuation can be in various modes like axial mode, bending mode, torsional mode, and so on. And a compact system can be, actuation system can be formed from it, and these materials are environment friendly. In fact, we saw that the nickel titanium alloy has good corrosion resistance, and power circuitry is not needed. However, there is one problem. Here the actuation is through heat, and this material has high heat capacity. So that's why the actuation is not so fast. It takes time to warm the material, to raise the temperature. That's why here the actuation frequency is generally around 1 Hertz. Now at the beginning of the course, in the first week, we saw comparison of different actuators made of smart materials, and we saw that in case of piezoelectric materials, the actuation force is less than the shape memory alloy, but the frequency is high. And in this case, the frequency is less, but the actuation force is higher. And the frequency is less because of the thermal mode actuation and high heat capacity. Now we will try to gradually understand what this shape memory effect means and how it is possible. Now to understand the shape memory effect or even serial SSD, we need to understand that this material remains in one of the two phases depending on the temperature, and these two phases are austenite and martensite. Austenite phase is also called parent phase, and they are high temperature phase. They are stable at high temperature. In the austenite phase, the material shows a body centered cubic structure that is shown here. So we have titanium and nickel. So nickel is at the center and titanium is at the corners, and nickel is at the center of the volume. Whereas in the martensite phase, martensite is stable at lower temperature, and martensite shows a phase centric crystal structure. So phase centric means here the nickel is at the phase center of each phase, not at the center of the entire volume. So it's a body centric structure which is shown by martensite, and this is phase centric structure which is shown by this was body centric structure is shown by austenite, and phase centered cubic structure is shown by martensite. Now this diagram explains the entire shape memory alloy behavior and the phase transition. So these are simplified 2D diagrams of the martensite and austenite variants. So this is a austenite structure in 2D. So these black dots shows the position of the atoms. So this is how it looks like in austenite. Again, it's a simplified 2D diagram, and this is how it looks like. So this is austenite, and this is how it looks like when it is martensite. Now if we compare these two diagrams, we can see that there is microscopically small difference. Here the structure this kind of structure is called a twinned structure, because if I take a line like this, with respect to this line, the upper part and lower part seems to be mirror image of each other, and this is called twin boundary. So it has a twin structure and this is a twin boundary. Now at this twin boundary, the structure does not break, it just shows a twin shape. Now if I compare the overall dimension of these two, so if this is L0, this is also more or less L0. So macroscopically they are same, although microscopically they are different. Now if on this twin structure some force is applied, maybe a shear force like this, then this twin structure changes and this entire thing detwins and it looks like this. Now if I compare this with this, then they are not even macroscopically same, they are microscopically also different. If this dimension is L0, then from here to here the entire dimension is L0 plus delta L. So, and this is also martensite. So in the martensite it can be twinned, so it's called a twin martensite, and this is called a detwinned martensite. Now if I have a shape memory alloy material in this phase, in twinned martensite phase, let's say that is our shape memory alloy wire that we saw before, and then if we apply load to it, so there is stress and then it deforms and it becomes twinned, and it can further deform after the twinning breaks. So the deformed shape, suppose macroscopically looks like this, so that is the deformed shape that we created. Now if we remove the load from it, it does not just go back here. So this deform seems to exist, this deformed shape seems to be maintained to some extent. So here we had a twin martensite undeformed, and then we applied stress to it, it became detwinned martensite, it deformed. Now if we apply heat to it, then on heating this material goes to this, the martensite phase becomes unstable, because at the high temperature the austenite phase is the stable shape. So if I apply heat to it, it transforms to a austenite phase and then it comes back here. So, and we know that macroscopically this and this look same, so again we get our original shape back. So that's how this entire shape memory effect comes into picture. So we started with this kind of a material, and that was martensite twinned, and then we deformed it, and that is martensite detwinned, and then we applied heat to it and it becomes austenite. And as we know that macroscopically austenite and martensite, they look same. So although by heat actuation it regains its original shape, but it does not go to the twinned martensite phase, because it's at the higher temperature, and at the higher temperature the stable phase is the austenite phase, but macroscopically they look same. So that's what it is. So we have martensite twinned, we have martensite detwinned, and then we apply heat to it and it becomes austenite. Now from this austenite, if we want to get martensite twin structure, we can just cool it down, and when it cools down the austenite phase becomes unstable and the martensite phase becomes stable, so it becomes a twinned martensite. So if I cool it down from here, it will go back to the twinned austenite phase. So it is twinned and it is detwinned. Now if we take a martensite which is already detwinned, and if we keep applying stress to it, then a stress level comes at which one layer slips over the another layer, and it can be seen here. So we can say that these two layer is slipping over the third layer. So these two layer just shears off, and that is called slipping. So for slipping to happen, we need even higher stress. But once it has gone to this range, once it has slipped, this cannot be recovered. So it's a permanent deformation. So this is all about the shape memory effect. It explains how the material remembers its memory, or what it means when we say that the material remembers its memory, what are the different phases, how to activate, how to go from one phase to another phase. Now just one thing to remember, here it's a simplified diagram of a twin structure. Now there can be various types of twinning. For example, something like this is also possible. So this can also be called a twin structure. And then again this. And again this is in 2D. So if we think about a 3D structure, there can be several variants of these twins. So we have austenite phase, which is more of symmetric, martensite phase, which has less symmetry. If we want to go from austenite to martensite, we can go there just by cooling, and there is from austenite to martensite, if you want to go, we can go by applying mechanical stress also. We will see that. Now this austenite to martensite transformation is a displacive transformation. It is also called diffusionless transformation. So it's a diffusionless transformation. And that simply means, so displacive or diffusionless transformation this means that transformation does not involve large atomic movement. And that we can see here also. If we compare this phase with this phase, the amount of movement the atoms take place is not large. So they don't involve large atomic movement. In fact, the atomic movement magnitude is less than In austenite it is 0.18 watt per centimeter degree centigrade. Martensite it is 0.085. Again we can see it's less than half. Corrosion resistance it is similar to 300 series stainless steel or titanium alloys. Austenite Young modulus 12 into 10 to the power 6 pound per square inch. In martensite it is 4.6. Again we can see that there is a large variation of the Young's modulus between martensite and austenite phases. In fact, martensite phase is much more flexible than the austenite phase. Yield strength in austenite it is 28 to 100 into 10 to the power 3 psi. Martensite it is 10 to 20. If we talk about ultimate strength, it is 130 into 10 to the power 3. Elongation at failure 20 to 30%. And we have transformation properties, transformation temperatures minus 200 to 110 in degree centigrade. We will see what this transformation temperature means. And shape memory strain, as we saw that these alloys can recover around 8% of strain. Now, so this was a basic introduction about this material. We have seen what are the two special features of these materials and how phase transformation can explain one of these, the shape memory effect. Now gradually we will look into some mathematical formulations of the behavior of these materials, and with that I will finish this class here. Thank you. Phases depending on the phase transition temperatures and the corresponding mathematical formulation. Now to do this, we define a variable called xi, and this denotes martensite fraction. What it means is, when xi is equal to 1, the material is fully martensite. Xi is equal to 1 means a full martensite material. Martensite, and xi is equal to 0 means it is austenite, and when xi is between 0 and 1, this means partially martensite and partially austenite. So when phase transition takes place, if it transits to an austenite phase, xi becomes 0. If it transits to a martensite phase, xi becomes 1. And this entire variation of this xi can be shown by a graph like this. So all this phase transformation can be seen as a variation of xi, and if we say that the transition is happening through temperature, that means how xi is varying with time, and this kind of variation is shown by a graph like this. Now here are some key points. This we call MF, this we call MS, and here we call it AF, and we call this as AS. Okay, so there is one error in the diagram we have. So this is xi and this is temperature. So xi is varying with temperature. Now here xi is equal to 1. Now this diagram, when the temperature increases, follows this path, and when the temperature decreases, it follows this path. It means, suppose I have a material at temperature beyond AF. So in this region, maybe here the martensite fraction is 0, which means the material is entirely austenite. Now if I reduce the temperature, then while reducing it will follow this arrow, so it will follow this path. So till it comes to MS, it will maintain xi is equal to 0, which means it is still fully austenite. There is no phase transformation. Now when it crosses MS, and if we further reduce the temperature, xi starts growing up and gradually it becomes 1 when the temperature is MF. So from MS to MF there is a variation of xi, and starting from 0 it becomes 1 when it reaches MF. If I further cool it down, it will maintain xi equal to 1, which means below MF the material is fully martensite. Now if we start increasing the temperature, it will not follow this path, it will follow this path, which is shown by the arrow pointing towards the right side, and till AS, which we called austenite start temperature, xi will be maintaining a value of 1, and after AS the value will reduce and it will become 0 when it reaches AF. So here we have now 4 quantities AS, and that is called austenite start temperature, and we have AF, and that we called austenite finish temperature. And then we have MS, that is called martensite start temperature, and then we have MF, and that is called martensite finish temperature. Now this behavior, as we can see that when temperature increases it follows a certain path, when temperature reduces it follows a certain path. So it is a path dependent behavior. So to know the amount of martensite quantity present, the martensite fraction, just knowing the temperature is not sufficient. For example, if somebody tells me that the value of the present temperature is between MS and AS, then if it is here, it can xi can be 0. If it is here, xi can be 1, and that depends on what the temperature was before. So if the temperature was more than AF before and it has been cooled down to this temperature, which is between MS and AS, then we can say that xi is 0. On the other hand, if the initial temperature was if the initial temperature was less than MF and it is heated up to a temperature which is between MS and AS, then xi is equal to 1. So it is here. So it is path dependent, it is history dependent, and it is hysteretic. So it is a path or history dependent behavior, and it shows hysteresis. And this is martensite fraction versus temperature behavior. Now we will try to fit some equation here, and again we can see that this part of the graph, it is just a constant. So here xi is independent of temperature till As. In this part of the graph, again it is constant, xi is equal to 0, which is that is at ms and beyond, whereas this part between ms and as and this part between ms and as and af, so this part between ms and mf and this part between as and af, they show some curved variation, and we need to mathematically model that. So to do that, so there are different types of curves that has been fitted to it. Here we will talk about a curve that is based on cosine function. So what we do is we consider xi to be a function like this. So it is C1 cosine alpha m t minus mf plus C2, and this is for austenite to A to M transformation, austenite to martensite transformation. So this is how we model the graph. Now all we need to know is the value of C1 and the value of C2. So if we draw it once again quickly, so we have MF here, we have MS here, we have AS here, we have AF here, and these are the paths. Now we are interested in modeling this graph, this part of the graph, and we are modeling it by cosine function. So when the temperature is Ms, which means, and we are considering austenite to martensite temperature, that means it is following this path. So when the temperature is Ms, the fraction of martensite is 0. So T is equal to Ms, that tells me that xi is equal to 0, and then if we put the values C1 cosine alpha m ms minus mf plus C2, and also we have one quantity alpha m here. Alpha m is pi by ms minus mf. So alpha m is pi by ms minus mf, so this quantity is just cosine of pi, so this becomes 0 is equal to minus C1 plus C2, because cosine of pi is minus 1. And then if we put the other condition, which is T is equal to mf, and at T is equal to mf, the material transformed to martensite, which means xi becomes 1 here. So xi is 1 here. So we have 1 is equal to C1, and then we put T is equal to mf. When we put T is equal to mf, this quantity becomes 0. So it is cosine 0, which is 1. So it is C1 plus C2. Now we can solve these two equations and find out C1 and C2.